All right. So this is PowerPoint 12, if you want to pull that up. We're going to start off with something called Kirchhoff's law. Before I do that, though, we need to understand what it means to be in a circuit, because I actually don't have any slides describing that, because they're not thought that circuits need to be explained, but they do need to be explained because they're very different from static electricity. So as you know, in a circuit, there's always a power source, right? And the power source is sometimes a battery, sometimes it's plug or a generator or something that's giving it some kind of voltage differential, right? So having a voltage differential is what drives any kind of circuit, right? And what does it mean to have a voltage differential? You guys should know this stuff because your test is on Friday. So if I had to ask you what is a voltage differential, you would say something like, yep. It has to do with potential energy. Is there potential energy if there's no charge? There's a voltage, but there's no charge. Is there potential energy? No, there isn't, all right? Because remember, voltage is potential energy per charge, right? So, okay, now you have this voltage source, such as a battery, and a battery releases one electron. What's going to happen to that one electron? It'll move from where to where? Exactly, and which ends are they? If it's an electron. Exactly, so the electron current will go from the negative part of the battery and follow the positive, because remember, a battery is not connected, right? So if I could draw the diagram, it looks like a capacitor, the longer one is always a positive, the shorter one is always the negative one. And there is no connection here. In between these two parts, there is no connection. So really, the only way that the electron can go and come to the positive is if there is a circuit. So it comes back and ends up on positive. Okay. Now there is something that physicists kind of messed up, and we just kind of kept it that way because it was too late to change anything. So we discovered circuits and all that stuff, and we characterized them. We described them in a lot of detail. We had theses about them, and then we drew them. And we had all these complex diagrams that might look like this. By the way, by the end of this course, you should be able to analyze that kind of circuit. Just kidding. But when you look at this, we just totally said that it's the electron that moves. And you're right, it is the electrons that move, the protons that move away too huge and they're part of the matter. So that's the part we kind of messed up. Every book, theory book, textbook, black book, whatever, describes a circuit as actually going in the other direction, right? As a positive charge being the thing that's moving. And that's not true. So we kept it this way out of convention, but please know that in reality, the electron is going the other way, not the proton going this way. Okay? So we're always going to draw it like this, but it's the opposite of it. Yeah. So there's a voltage difference, right? So if this is 9 volts, and this is 0 volts, so this is a 9-volt battery, right? So therefore, any particle that you would release here, such as let's say an electron, right, is going to have potential energy to do this. And that potential energy is going to turn into kinetic energy to be able to follow the circuit and to reach here and then lose all this potential energy. Okay, so it leaves with a full amount of potential energy, comes back in with no more potential energy. Okay? It's the potential energy that drives the motion of this. Now, a current is exactly that. It is the movement of a charge, or if you can measure it as charges per second. Okay, again, I don't have anything that describes that, but it's current is just charges per second. And in a circuit, charges always move as long as there is a place for it to move. Okay? So you won't ever have a charge and then just stop there. Okay? Because then that becomes static electricity. That's not what we're talking about anymore. Right? So this is really a current and it goes from the negative to the positive, or from now on, I'm going to say from the positive to the negative. Okay? Any questions about that? Okay, great. That's what a circuit is. And we're going to talk about them. We're going to start with some more basic stuff. Who remembers some basic components of circuits that you might have learned? Possibly. Nobody? Sure you remember. Yeah, there is a resistor. Yeah, okay. So do you want to answer me with that? There's sometimes a switch exactly to cut or to make the current go or to stop the current. I like the idea of amperes. What are amperes? Joules per coulomb. Nope, that's voltage. It's coulomb per. I just defined it. Coulombs per. Remember, current is the movement of electrons. Yeah, coulombs per second. Okay, those are what current. That's what amps are. Yeah, so there's going to be a certain current inside a circuit, and then this current is carrying a charge across, and it's taking the charge a certain amount of time to get across. And you can have more charges per second, and that'll be a bigger current, or less charges per second, and then you have a smaller current. Then we have resistors, which is the whole point of a current, because if we just have this game here, where we send our electrons from one end to the other, well, whoop-de-doo, why the heck do we want to do that? So the fact that that potential energy is becoming kinetic energy, you can utilize that to do some kind of productive work, right? That potential energy lost from leaving the negative and entering the positive, you're gaining some functional, some useful work. And so we use that to light up a light bulb, to calculate things for us, to do anything that a circuit does for us is being done because there's a voltage difference and that potential energy is being converted to useful work. Okay? So we're going to start off with something called Kirchhoff's rules, or Kirchhoff. I don't know. When you guys learned this, did you call it Kirchhoff or Kirchhoff? Did you guys even learn this? No? No one learned this? Yeesh. Maybe you learned it, you just don't remember what it's called, or you're never told what it's called. So, okay, that's what we're going to do today. We're going to talk about Kirchhoff's rules. He's got two rules. They're very, very simple, and they're kind of intuitive. There is a kind of a gory analogy that this, because I'm using Mr. Wakarski's slide, so I decided to keep it just because some of you guys are into violence and stuff. But anyway, we'll get to it. So here I have a circuit. It's a very simple circuit, all right? It's got a couple resistors. What could you tell me about this circuit? Tell me some keywords that you might remember. Dig deep. It was 3 years ago. 3 years ago? So all of stage up one, all of that. Yeah, about 3 years ago. Mark? Uh, maybe. We actually don't have enough information to make that deduction. Yeah, Bronwyn? Correct. So remember these words? Series circuit and parallel circuits? Yes, they're coming back. Which one is this? William? This is a parallel circuit. You can write that down. Yeah, parallel circuit. By the way, just real quick, if possible, because I just realized that it's not always possible, when you do your lab reports from now on, if possible, please do them in Word. The reason for that is because writing in Word is a lot easier to correct, to write on the document than it is in a PDF. Now I know that some of you don't have Word, so don't bother if you don't have Word. Warning. But if you do have it, it really does help me a lot if you use it. Okay. So the majority of you doing Word would help. Yeah. No, you can't because you have to submit it to Moodle, and Moodle doesn't accept Google Docs. I don't think. You can try, but I don't think it does. Yeah. All right. Okay. So this is a parallel circuit. How do you know it's a parallel circuit? So William, you said it. What's the characterization of a parallel circuit? They don't add up. That's what the definition of a parallel circuit is. But how did you know that this is a parallel circuit? Okay, so William is saying that these three resistors are in parallel because they're geometrically parallel. That's not necessarily the right answer. That's not why they're parallel. If I had a current going here, what's going to happen to that current? Exactly, it'll split, all right? And that's the definition of a parallel circuit, is where there is a node, and then we call this a node here, right? There's a node where the current coming in is split into multiple currents going out, or vice versa, right? So it could also be that you have current coming in, and only one current going out. And there's a node right there. Okay? Is there a node here at 3? Yes, there is a node at 3. Is there a node at 6? Yeah. Is there a node at 4? No. Okay? So there is no node at 4 because this current has no choice but to go in that direction. Okay? That's like saying there's a node here, and that's not true, right? So no node at number 4. Is there a node at number 5? Neither. Okay, so your current goes true. All right, so there are nodes in parallel circuits. In a series circuit, there would be no nodes at all, and the resistors would kind of just be like in sequence, right? Any questions about this? Does this ring a bell? You guys learned this, right? Yeah, okay. So Kirchhoff's rule says that in a parallel circuit, the amperage going into a node and coming out of a node have to be equal. Okay? I'll go back on my diagram and I'll tell you what that means. I'll let you guys write this. So if I go back here and I looked at node 2 and I said the current coming in, I'm going to call that I1, right? I'll just wait a couple more seconds because I want everyone to see this. All right, so the current going in at I1 is coming out at, I'm going to call this one I2 and I3, right? And if I were to write that, what would the rule 1 say? That the current going in must be equal to the current coming out. How could I write this up in an equation? Yeah? Yes, exactly. I1 is equal to I2 plus I3. That's Kirchhoff's first rule. Okay, and it works for any node. As long as it's a node, it's going to be fine. If there was a branch, if I had one current coming in, and then 3 currents coming out, and I call these 1, 2, 3, and 4, then current 1 would be equal to current 2 plus current 3 plus current 4. Okay? And if I had many currents coming in, then I would add them up on the left side, and they would equal to the ones coming out, right? Think of it as a flow of water, right? Anything that flows into the pipe has to flow out of the pipe, okay? This because it looks messy. All right, so that's the first rule. Then for voltage, is that the voltage difference across each parallel part of the circuit is going to be equal. So if I were to go back again, wait until you write it. So the voltage drop is equal and constant in a parallel circuit. This is his second rule. So if I were to go back here, I would be able to tell you that since these 3 parts of the circuit are in parallel with each other, if you were to take the measurement of the voltage at their respective nodes, so for this first part of the circuit, right? So this circle here, for this circle here, if you took the voltage difference across 2 and 7, then it should be equal to the voltage difference across 3 and 6,
and the same as the voltage difference across 4 and 5. Okay, so here is saying that V27 is equal to V36, and that's equal to V45. And if they're all equal, and the total voltage is 6 voltage, then they are also equal to their total voltage. So in this case, it's going to be V18 or 6 volts or however you want. Any other questions? Okay. So that's Kirchhoff's rules for parallel circuits. It's the opposite for series circuits. All right. So for a series circuit, the current's going in through the resistor is a current coming out, and that's kind of intuitive because there are no nodes, right? So if I had something that looks like this, right, my current is always going to be the same because there are no nodes. So I1 is equal to I2 and is equal to I3. If I had this connected to a battery, like that, and this is a positive terminal and this is a negative terminal, and there's a certain amount of energy that's allowing my electrons, or I'm going to say my currents now because I can't say electrons, it's not true. There's a certain amount of potential energy that's allowing my currents to go in this direction that I've indicated by this arrow. And after it goes through a resistor, some of that energy gets lost because it's done some work, right? Whether it's lighting up a light bulb or causing something to heat up or whatever, so you lose some of that potential. That means that the potential decreases after every single resistor in a series circuit, right? So if this were V1, this were V2, and this were V3, then they would not all be equal. They would actually add up to become the total voltage. So in this case, you can say that the total voltage starting from the battery is equal to V1 plus V2 plus V3. All right. So those were Kirchhoff's third and fourth rules. They're kind of like the first, second rules, but they're just only apply for the series circuit. And we got all of Kirchhoff's rules right now. And you've learned all of these, right? None of this is still new, hopefully. Good. You grade 10 teacher did a good job. Who was your grade 10 teacher? What's her name? And if you're on CNN, is it her name? Monsieur what? Monsieur Boyer. Okay. And Moyer. Boyer. Okay. What's his first name? Nicolas. Okay. I don't know if I've met him. Okay. Is that the only teacher? Who else? Monsieur what? Cool. Here we go. Series circuit. And you can see that the current has only one direction to go to. So the current remains constant all throughout, right? But the voltage is going to drop after each one of those resistors. So that at the end, when you reach back at the end point, your potential energy left over from your current is how much? How much is left over at the end? You start off with 12 volts. How much do you end up with? 0. Yes. Say it loudly. It's okay. 12 volts, all of it's going to get run down to 0 volts. And where do those volts get run out? Well, the current going into here is going to decrease that voltage each time to the point where after the last one, there's 0 volts left. Yeah. Okay, so if I were a current, right? If I'm entering this node here, right? If I haven't entered the node yet, I would have the same amount of potential going there as I would do there, because once I commit to it, I can only go through one of them anyways, right? So my energy loss is only, let's say I go through this, I mean, it's getting really messy now. Let me change colors. Let's say I'm a current, I'm going this way, okay? That current has the same potential energy as a current going this way because a current can only go through one of the ways. So the one it picks is going to be the one that's going to cause it to drop. But they're not all going to make it drop because you don't go through all of them. You only go through one of them. So think of it as like your option. Let's say you have $10 to spend on. Yeah, exactly. At the end here, it's still going to be 6 volts and 0 volts. It's just how you spend your volts depends on which route you take. But you definitely are not spending them on all three. Yeah. Okay. Good. That was a good question. Okay, so let's do some practice. This is a really hard example for some reason. Why would I put this first? Should I or shouldn't? Let's do this first and then we'll come back. Okay, so let's talk about resistors. This is also something hopefully that you remember, that if you want to calculate the total resistance of something, then it is equal to, in series, so this one is in series only, it's equal to the sum of all the resistors in series, right? So if I were to write it down, I have a series of resistors, and I can rewrite that as one sum of those resistors, okay? So writing these two things, like these images on the left and on the right, they are exactly the same in terms of the circuit, okay? So if I have two 2-ohm light bulbs, it would be the same, if it were in series, it would be the same as having one 4-ohm light bulb, for example. But I guess I should mention that resistance is measured in ohms. You guys remember that unit? There's no apostrophe. It's just. Okay. So here it is. If I want to look at REQ, so REQ is the equivalent resistance for the circuit, and it's summarized by if you were to combine all the resistors into one resistor. So in this case, there is only resistors in series, and if the resistors are in series, you add them up. In this case, they're all equal to each other. They're all called R. So in this case, REQ is going to be equal to 4R, otherwise known as R plus R plus R plus R. Okay. In parallel, you guys remember this equation? So you have to inverse them and then add them together. So the REQ is always going to be lower than the individual R. Always. Right? I'm sorry. Oh, sorry. I gotta turn off the auto rotate. Has it been doing that a lot? No. All right, so here, REQ is always going to be less than R1 or R2 or R3, etc. Okay? So for this example, REQ, EQ is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and all that to the negative 1. And they could look differently, so you can see different versions of what a parallel circuit might look like. What you need to identify when you're looking at a circuit is where are the nodes, right? If there are nodes, then it's a parallel circuit. If there are no nodes, then they're parallel circuit. Yeah. Well, okay, so I could write it differently. If I didn't write that, I would have to write 1 over REQ is equal to 1 over R plus. So instead of solving for 1 over REQ, I'm just solving for just REQ. Yeah. And you might have different terms for REQ. So I'm calling it the equivalent resistance. Then some people call it the total resistance. It's the same thing. Okay? Perfect. Now we got our tools to solve that hard problem. So let's go back and do this. All right, so I'm asking you, I still didn't even show you guys Ohm's law. So how do you solve this without Ohm's law? We'll come back to this even later, actually. We need Ohm's law. So here it's asking you to find your equivalent resistance. So we'll do this one together. And so you have to imagine that your voltage goes from A to B. So that's going to be our voltage source. And it doesn't matter which direction we choose to be the positive or the negative in this case, because they don't even indicate it. But now if I were a charge going in this direction, where is my first node? Yeah, so if I'm a current coming in this direction, where are my options? So 30 and 45. So I have the option of going there. I have the option of going there. Do I have any other options? No, I don't have the option of going there. Why not? I do. So I have the option of going into 3 places. So that means I have three parallel possibilities. Now these two are parallel to this one here. So let's find the equivalent resistance for just this and this. So 30 and 45, let's find the equivalent resistance for those two. So it would be 1 over 30 plus 1 over 45, and all that to the minus 1. And tell me what you get. 18? Okay. Microsoft PowerPoint has stopped working. That sucks. I'm going to lose all of those annotations. Maybe if I try to recover the information. Oh, Microsoft PowerPoint's restarting. Am I going to get it? Oh, yes, I got it. I think it's going to crash again. This is a bummer. Ay. Technology. Oh, give me 1 second. Oh, yes, there we go. Okay, so you guys said 18? Everyone agrees with that? 18 ohms. All right. That means I can rewrite this circuit. So keep this slide up, and I'm going to go to the next slide and show you what it's going to look like. So now I have something that looks like this. Because I've combined these two circuits, I've combined them into one, right? So I collapsed, I think I have one too many branches actually. Yeah, I do have one too many branches. Reverse this one. Like that. All right, so I've combined them into one, and this is the one that I combined it into, and this is my new 18 ohm circuit. And I could rewrite the other one, so it's going to be 42 here and 40 here. And next, what I can do is I can look at this branch and look, oh, hey, look, those are in series, so I can combine those as well. So let's combine those. Are they in series or are they in parallel? Series, so you just add them up. So REQ in this case is going to be equal to 42 plus 18. Big math here. Oh boy, 40. Okay, 60. So I got my 60 ohm resistor, and that means I can rewrite my circuit now as following. Ugh. And this is a 60 ohm circuit resistor, and this is a 40 ohms resistor. So how do I collapse these into a single one? Is it series or parallel? Parallel. So I could do, again, the new REQ is going to be equal to 1 over 60 plus 1 over 40 to the minus 1. Here's a hint. Remember I said that your REQ in a parallel circuit is always going to be lower than the resistors? So if you get something higher than 60 or 40, you know you've done some wrong math. Anyone have a number? It should be like 18 or something. I don't know. $24? 24 ohms. You know you did this correctly because the sum of the equivalent resistance is less than each of the two parallel resistors. And then this is now the same as writing just one resistor of 24 ohms in magnitude. Okay? So we took a complicated circuit like that, started off like this, we turned it into the most simple possible circuit that we could imagine. Just one resistor. Right? Did you guys do that in high school? Yeah, so far you've done that as well. Okay, good. We're going to do some more complicated one. But yeah, so far it's pretty much the same. So I want you guys to do this one. Find the total equivalent resistances for this complex circuit. Try to figure out what's in parallel with what, and then combine them to create one. In the end, I want a circuit that looks like this. That's the other way around the battery. So work on that and try to give me a equivalent resistance. Have you guys seen Marco or Michelle today? Do you know if they're coming? No. So go ahead, work on that. try to make a little pathway for your current. You like pretend you're the current that goes, oh look, I have 2 forks to go in the road. Where do I go? And then you choose one and you follow it up until you get every single possibility, until you've hit every single resistance. And remember, you're always going, you're a current, you're always leaving the battery, and your desire is to get back to the battery on its other side as fast as possible. What's that? Basically, what you don't want to be doing is going like, what currents definitely won't do, like, right? So if it goes like this, it's going to come right back. If it goes like this, it's going to come right back. If it goes like this, it's going to come right back. Okay? It's always going to come back to this battery. Well, what you're trying to do is find one equivalent resistor so that the circuit only looks like this. Okay, so that means that you have to figure out which one of these are in parallel, which one of these are in series, and collapse them, and keep finding, kind of like what we did in the previous problem, until you only have one resistor remaining. Yeah. Which one? Yeah. Yeah. But if you look at it, that 5 on the top right, and the 5 on the far right, so that 5 and that 5, you are currently there, you have a choice of where to go. So these are actually series. So I would start with collapsing these two, combining these two into one. Yep. No, because there are some that are in series. You can't, you could, but you have to collapse the series one first to make them all into parallel. So this one here, if you have a current going in that direction, these two are in series, right? And these two being in series are going to be in parallel with this. So how could you make this and this a parallel if you didn't combine these first? Yep. You have an answer? Where's your work? Oh, that's your work. I don't know the answer. Keep it in mind, okay? It is, except we have some series circuit. Otherwise, all parallel, I'd say you're 100% right. But I'm not sure. We'll have to wait. I haven't done the work yet. So while you guys are working, I'm just going to do that first step like I talked about. I'm going to go on the next slide for that. You don't need a whisper. It's group work time. So I've done the first step. What would be my second step? Someone figured it out yet? Johnny, what would you do? Yep, exactly. So take these two and add them in parallel. Because that way they're going to be in the series with this one. So I'm going to do that. So 1 over 10 plus 1 over 10 is going to be equal to 1 over 5. Do that to the inverse, then I get 5 ohms. So my circuit should now look like this. What am I going to do next? Which ones am I going to combine? 5 and 5? Very good. So let's do that. So 5 plus 5 is 10. You have a question? And so I can combine these two now. It's the same as doing it in step 2. So it's going to be 1 over 10 plus 1 over 10 minus 1 is going to be equal to 5. And then I add these two finally. Give me 5. Sorry, 10. And now we have the most simple possible circuit that we can make out of these resistors. Okay. So far, so good. Do this one. You done? Could you tell me the equivalent resistance for what I circled there? 3? Did you get something like this? Question, what is this here? A battery. Is it a battery? There's two batteries. Two batteries connected in series or parallel? Series, because they're head to tail. Okay. So when I have two batteries connected in series, do I add up their volts or do I add up their current? Yeah. Why are they? Well, they could be anything actually. I'm saying batteries because there's two of them, and you don't normally have two power supplies. But it's a voltage source. Yeah, I'm calling them batteries. We haven't learned that yet, so stand by. There is something. So you guys have like your calculators, for example, your TI-83s. They have 4 batteries, right? So are those 4 batteries connected in series or 4 batteries connected in parallel? And what does it mean to do each? One of them gives you more power, more energy. The other one makes your batteries last longer. I'll let you figure that out. We'll learn that in a couple of lessons. Keep going. So now it's getting tricky because you don't know exactly which ones to start with. Someone have an idea of what to start with? Which ones? On the right? So this one and this one? Yep. Start with those. So if I combine them, I get one equivalent resistor of 2 ohms. Now which ones do I do? Which one? Doing the 4s. So if I was a current coming in here, what are my options? I can continue going around and going into my 2. Oh, oops, erase that. I can continue going there. That's one option. Where's another option? Down and where? Down and left, let's say, that's one option, and down and right is another option. So in fact, these 3 now are in parallel. You can combine those all 3 at once. Yep. Yes, it does. Actually, doesn't matter. 1 plus 1 over A plus 1 over B. Inverted, it's going to be 1 over A plus B. I don't know if mathematically makes a difference, actually. It might give you the same answer. It's important to recognize, though, that the three are in parallel together. So that would be 1 over 4 plus 1 over 4 plus 1 over 2. So does give you the same answer? Okay. So this should give you 1 ohm. So therefore I can knock these resistors out and just replace it with one resistor of 1 ohm. You okay there, William? Can you see from there? Okay. I have it on Adobe Connect if you want to pull up your laptop. What's my next step? Mark? Exactly. So add these three now. They're in series, right? Yeah, very good. So that's going to be 6. So now you have one equivalent resistance of 6. Like that. And lastly, we add the last two that are in parallel. I'll give you a hint. Whenever you have two parallel resistors that are the same value, the equivalent is going to be 1/2 of that value. Okay, so if I have two 6s, I can combine that into 1 3. You guys get what I'm saying? Okay. So my final circuit is going to be a 12-volt battery connected to a 3 ohm resistor. Yep. Okay, so there was a 1 ohm here before, right? And this one, and this one were in series. So I just add them together. If it helps, definitely keep redrawing the circuit with the new resistors. All right, this is really, really messy. So give yourself the space and time to just draw yourself the new resistors so that you don't make any mistakes that have to do with confusion or anything like that. Is there more? This is a trickier one. All right, you must create a 5 ohm resistance, but you only have 10 and 20 resistances available. How would you create it? You can use as many 10s and as many 20s as you want. Yep. Exactly. That would work. 10s, ohm, 10 ohm. So you do 1 over 10 plus 1 over 10 minus 1 is going to be equal to 5 ohm. What if I had 1 10 and 2 20s? How would you make it happen? So I had 1 10 ohm resistor and 2 20 ohm resistors. What's that? All in parallel? So let's try that. So why don't you guys go ahead and give this one a try? Is it even possible? Now that I'm thinking about it. Yeah, I think this might give you the right answer. Yeah. So yeah, we can definitely do that. When you guys buy your circuit kits from Tanya, you'll see that you only have certain resistor combinations because they only manufacture resistors in certain multiples. We'll learn about how to read a resistor later, maybe even today actually. But you'll see that resistor has got color codes. Have you guys learned that? Yeah. So if you remember, like a resistor, what it looks like a little tube. It's got two LEDs attached to each side, and on the resistor itself, it's got some bars, and those bars actually mean something like a distance convention. And you'll be able to look. What should we do here? Let's take a break. Come back in 5 minutes. Yep. Pull it up. Were you going to be doing it faster? Okay, show me the numbers of that. What velocity will it have? I think when you use the field force connecting on the charge, what is it you use to do to? This is a very simple question. The tutor wasn't able to solve it? General tutor. Okay. To get, let's go to the board. Let's say you start off at 100 volts and you end up at 55 volts. Right? You have a voltage drop. Doesn't matter what happens in the middle. So we're going to put the beginning and the end. You have a voltage drop of 45 volts. Okay? And if you multiply that by your charge, and the question is going to show you what velocity will it at point. Show me the question on my slide.
Okay, we're going to the dot.
What velocity protons. The proton. That's your charge. Okay. So your proton times your voltage is going to give you a potential energy on your work. All right, and that potential energy becomes kinetic energy. So this potential energy, Q multiplied by 45 volts, is going to become kinetic energy. And so this is your velocity that you solve for. Which one? Kinetic energy? That's because it's not from this year, that's from last year.
There's one of the equations from last year that
Not the ones that directly relate to us. These are math ones. Okay, show me.
Yeah.
Okay. All right. Okay. There's 6 things, are they correct?
Yeah.
Because I thought it was 2 numbers after this. Anyway, it doesn't matter. Okay, so I'll give you guys the marks. How much marks I'll pay for that? Okay. What program did you use to draw those lines?
Yeah, it's about ethics.
FFC?
It's nice, right?
I can't believe, did it do it mathematically or did you just draw it? And
No,
then
I
it turned it,
just draw it.
and then it turned it into that or kind of thing?
Yeah.
Because you didn't have your steady hand to do that.
No.
Okay, cool.
Yeah, just draw a line. After I curve the line.
Okay. Yep.
What I thought, yeah. Can you just say Yep. Can you try it again? Oh, I see. Can you open like an incognito window? So can you switch your browser? It still keeps you logged in. You're on Explorer.
No, I'm on Google Chrome, but I opened.
Try it. Can you show me something? I have a suggestion for you. For you, I don't know, go see JP.
If anything, I'll just make her submit it every time, just so that we can actually see them.
That's not a long-term solution.
No, but. I'm gonna just do like maybe 20 minutes of stuff and then you can shut this down. All right, let's continue again. This is that analogy that I told you was kind of gruesome. So Kirchhoff's law, you can think of it this way. If your moving charges are represented by soldiers going out into war, the unit is ampere. So the number of soldiers that you have going out to war are a certain number, right? And then you have the electric potential or their voltage, which relates to how much bullets each soldier carries. All right, so now you have X soldiers, and each soldier has Y amounts of bullets, right? And then they go off into their mission, and then they come back. When they come back, your soldiers all come back, your currents all come back in an ideal world, right? And in an ideal world, not in an ideal world, when they come back, their ammunition is depleted, so they have no more bullets left over, but all the soldiers come back, neither of which is true and both of which is quite sad. But the point is that they go off, they deplete their energy, they come back without their energy or their ammunition. Who can come up with a better one? That one's so 2010. You can say like, you send off Girl Scouts with Girl Scout cookies, and all your Girl Scouts come back, and hopefully they've sold all their Girl Scout cookies. That's a good one? Okay, yeah, let's stick with that one. All right. All right. So that's what that is. I'm not going to ask you to do this one yet, this practice problem set yet, because you need to learn about Ohm's law before you're able to do any of that. All right, so in order to properly analyze a circuit, we need to understand something called Ohm's law. And Ohm's law, again, is one of those ones that you know. Here. I want you guys to open up PowerPoint number 13 now. And this is a short one. It's not very long. It's 10 slides with some problems on it.
You gotta do this every single time. It's so annoying. Okay, so Ohm's law describes what's happening with that current at each specific point. You have to remember one thing in Ohm's law, and it's this. The voltage is equal to the resistance times the current. You can do this for the total circuit, so you can do the voltage of the total circuit, for the resistance of the total circuit, to get the current of the total circuit, or you can do this for each individual resistor. So you can say the voltage of a certain resistor is equal to the resistance of a certain resistor multiplied by the current of that certain resistor. So it works for globally and it works for locally. Okay, that's what Ohm's law is. That there's this relationship. Okay. So because the voltage is usually constant, so when we use a battery, that's called a constant voltage source. When you plug it into a wall, you have a constant voltage source. So your voltage in general doesn't normally vary. So what ends up varying in your circuit is the current. All right. So if you have a strong resistor, it's going to draw in more current to make up for it. Okay. Sorry, the stronger the resistor, the less the amperage is going to be. So now the voltage, we have the tools to find the total resistance. We have the tools using Kirchhoff's law to find the total current. Remember that in a series circuit, the current is constant, is always staying the same. And in parallel, the current splits and adds back up. And we also have Kirchhoff's laws in terms of voltage. So we know that in a series circuit, the voltage drops, but in a parallel circuit, the voltage stays constant across the parallel parts of the circuit. Okay? And so we have this here, and now we can find the total current and all that stuff because we have Ohm's law. So the first thing I want you guys to do is convert this into an equivalent simple circuit. Okay? So this is exactly what we just did before the break. So I want you guys to go ahead and do that with this problem. So I would combine those first because they're in parallel. 1, 2, 3, 4, 5, 6, 6. Give me 6 ohms, I think, for these three. No, I'm wrong. 3? Is it 3 ohms? 3 ohms. All right. So now I can get rid of all those 3 and combine this to get a 3 ohm circuit. And now I have these 2 in series, so I can add them up. So 12 plus 3 is going to be equal to 15 ohms. So I have now the total. I'm just going to wait until you guys are done writing because this next part is very important. I now have a very simple circuit with one resistor, one voltage source. So that means if I have it at this simple situation, then I could find the current going through that one simple resistor, right? And the current going through that one simple resistor is going to be the current that goes throughout the whole circuit. That's the I. So let's find that. So we're going to say that V is equal to IR, or RI, however you want. So V is equal to IR. Do you guys remember this formula from when you were in high school? Yep. Okay. So my voltage is 30 volts, and that's equal to my total current multiplied by Req, which is 15 ohms. So therefore, my current I is equal to 2 units amps. Right? Okay. By the way, just if you're curious, 1 amp is equal to 1 coulomb per second. Okay. It's like the speed of charge. Okay, perfect. I have my current that's coming out of my battery, and the current coming out of my battery is 2 amps. And if I go work my way backwards now, all right, and I have my current that goes through this 15 ohm, and if I broke it back up into its two constituting ohms, resistors, so if I were to remove this 15 one and bring back the 12 and the 3, what's the current going in each of those two resistors? So remember, what happens to the current when we're in series? Two resistors in series. They're equal. So if I had 2 amps coming out of here, then it's 2 amps going into this resistor and 2 amps going into this resistor. Right? So now tell me, what is the voltage dropped for each of these two resistors? Check it out. I have the resistance and the amperage for each. Resistance and amperage for each. So if I have resistance and current, so if I have R and I, can I calculate V? Yeah, you could. Let's do that. So 3 times 2 is equal to 6. And 12 times 2 is equal to 24. Do you guys notice something? Yeah? Yeah. The voltage equals the total voltage. So remember, before I was asking you what happens to your voltage? Actually, I wasn't asking you. Never mind, forget that. So what you can notice here is that the voltage drops. So this first resistor uses 6 volts of potential, and the 12 ohm resistor uses 24 volts of potential. And so if you're at 30, then you're going to be at 24, and then you're going to be at 0. So at this point here, your voltage is going to be 0, and that's great. Your Girl Scouts sold all their cookies, and you're back. Okay? Now, let's get it even more complicated. So we said here that it was 2 amps that went through this 3 ohm resistor. But that 3 ohm resistor is a fake made up resistor. There is no 3 ohm resistor. There is 3 parallel resistors here, which I can't actually just delete. I just conceptually remove them from my mind so that I can calculate an equivalent resistance. So I can actually find what the current is going to be in each of these. So you guys said that the voltage here and the voltage here, the difference was 6 volts. And I remember I said that in a parallel circuit, the voltage doesn't drop. So each one of these is going to have 6 volts across them, right? That means I can find the current in each one. So let's do that. Find me the current in each one of those resistors. Someone have an answer? Yep. What did you get for the 9? And what did you get for the 6? What do you guys notice? if you add them up, you get to 2A. And that was the current that passed through this resistor, this equivalent resistor to begin with. Remember I said that in a parallel circuit, the current splits up. So that makes total sense, right? You guys do it for this one. Which resistors would you combine first? Yep. The top, yeah, you would combine these to make one 80 ohm resistor. Then you combine these two in parallel, which would give you what? 40. And then you add them together and you get 60. Once I have the total resistance, what's the purpose of getting that total resistance? Why did I do all that? Why am I asking you all this? What is the meaning of life? What is the meaning of this problem? Find the total current. That's the whole point. V total, not VI, but V total, is equal to R times I. That's going to be 60, and this is going to be 12. So therefore, R is going to be equal to 0.28. Perfect. I have that current. Now what can I do with that current? What's the point of finding the current? Why did I ask you to do all this? Tony. Exactly. So I can now break up my circuit back up into its original, slowly break it up into its original situation. So I have, where was I before that? I had this 40, right? So I can find the current through both of those. The current through both of those is going to be 0.2 amps. Yep. You gotta work your way into the most simple circuit and then work your way backwards, right? That's the only way to do it, unfortunately. So that now is the part where we're going backwards. So I have to find the voltage for these two before I can find the voltage for anything else. Okay. So I have my current and my my resistance here, so I can find the voltage. So 0.2 times 20 is what? 4. Is it 4? Yeah, 4. So 4 volts. Do I even need to calculate this one? Because if I had a 12 volt to begin with, and I used up 4 volts, and there's only this resistor left, then I can just do a subtraction. 12 minus 4 is equal to 8. I mean, obviously, I can also just multiply them. That'll get the same number at 8 volts. All right, perfect. So that means that across this point and this point, there is an 8 volt drop. If there's an 8 volt drop, that means there was an 8 volt at the top and an 8 volt at the bottom. So let's figure out what the current is at the top and at the bottom, because the current's got to split. So my equivalent resistance here at the top was 80, and the bottom was 80. So my current is basically split in two. If I had a 0.2 amp current, what is going to be my split in two current? 0.1 amp, 0.1 amp up here. And if I have my 0.1 amp at the top, I can figure out what my voltage drop is going to be for each of those two resistors at the top. So now I can remove this. Is it 4? 4, 4. Not sure about that. V is equal to IR. So 0.1 times 30 is 3 volts. And here, 5. And that's good because they both add up to the 8 that was supposed to go across that node. Make sense? Is there another example? You guys do this one? While you guys do that, do it as well, but I'm not going to go over the answer. Ask me if you have any questions. Oh, I'm not going to get to do this in my head. Oh no. If someone's doing it, just tell me the number that I'm supposed to get. Thank you. Is this also something that you did in high school? No? Is everyone here from St. Anne? Who's not from St. Anne? Okay. So most of you. Who came from an English school? No one? Okay. But your English is also good. Because that means wherever you learned English, they must have taught it really, really well. Like, no? But why is... Oh, is that really the situation? Who believes that their school, that was not St. Anne, taught them really well in English? Ouch. Okay, so families. Thank your families. Being bilingual is literally the best skill that you can have in Quebec. My brother is a prison guard. Weird. Okay. Anyways, he works at Saint Anne des Plaines in like all the way in north of Terrebonne, and he's bilingual. He's a Bill 101 kid like me, so we went to French school. And because he works in such a predominantly French area, he's the only one who's bilingual, and he's the only one eligible for any promotion because it's a federal prison, and they only promote people who are bilingual. There you go. So good or not at his job, he's automatically like the best because of that. Okay, so once you have the total current, can someone give it to me actually? It should be like 1.8 or something like that. No, no one's at that point yet, total current? $1.94. And then I'll let you guys work your way backwards. I can't do this without a calculator. So, but I mean, it's a very similar to what we did before. I'm just going to jump ahead to see what we're going to do here. Should we do this one? Oklahoma. Yep. This one? Okay, sure. So if it's 1.94 amps here, it's also going to be 1.94 amps here. What's that? Oh, I have a total voltage of 8 and a total resistance of 4.13. What's that? So 4.13 is okay, so let's start from the start here. I delete everything. Combine these ones first. I got 3.33. Then I combined this 3.33 with this one, so I got 7.33. And then the 7.33 with the 3, I got 2.13. The 2.13 with the 2.0, I got 4.13. All right. I'm going to stop teaching any kind of new stuff now, right? And I want you guys to practice on some of these problems. So if you go to Moodle, there's going to be the practice problems for circuit 1. There are going to be some questions that you won't be able to do, and I'll open them up with you so that you can see which ones they are. So everyone go to Moodle. If you're still working on it, maybe just stop it for 1 second. You guys are going to go to circuits 1. I want you guys to do part 1, so part A, part B, and, oh yeah, you can do the whole first one. Do all of circuits 1, even though the document says circuits 2, it's actually circuits 1. It says Wheatstone, but I deleted the Wheatstone part. I don't have, let me see. Oh, look at that. If I look down here, oh, R3 has a voltage of 3.8. Oh, actually, yeah, you don't actually know. The answers at the bottom here are totally garbage. Show me your work. Okay, so do it and then show me. Yep. What's that? About the resistor stuff? We're not doing this now. After class. So you guys aren't studying, please, okay? We're working on this stuff.